We're going to look at bifurcations. Before studying bifurcations, let us quickly take a look at something which we had studied in the previous lecture, that is the stability of fixed points. So we had seen fixed points in the last lecture. So we have an equation x dot as some function of x, and that curve looks something like this, for example. Okay, so wherever the curve fx crosses 0, those are our fixed points. And now we had seen that if we have an initial condition over here, the x dot at this point is negative. As a consequence, this point will try to move towards the left. If we have an initial condition over here, the x dot at this point is greater than 0, and so the point tries to move towards the right. Essentially, all the points in this place, all the points in this space and all the points in this space, they are attracted towards this point, this fixed point. Whereas if we have a point over here, the x dot is positive, so it tries to go over here. So this point is also an attractor. This point is a repeller because point over here tries to go towards the right. A point over here tries to go towards the left. So this helps us in defining stability of fixed points. So there are some fixed points which attract like these, and there are some fixed points which repel. What dictates whether a fixed point attracts or not? It is quite obvious that the slope over here is positive, so it's a repelling point. The slope over here and over here is negative, and so it's attracting. But let us try to prove that. And while this is not a course for the theoretical aspects of all this, but I think this is something which would help us in the future. So let us consider the behavior of this equation near a fixed point. So let us denote the fixed point by x star. So let us consider the behavior of the difference of x from x star, that is the behavior of x in the neighborhood of a fixed point. So it is in the neighborhood of a fixed point. So d eta dt is going to be equal to dx dt minus dx star dt, and dx dt is equal to f of x, while dx star dt at a fixed point is f of x star, and it is 0 because it is a fixed point by definition. Okay, so now let us write f of x in terms of a Taylor series expansion. So x, so this can be written as f of eta plus x star, essentially, which is f of eta plus f of or we can write it as this. So f of x star plus del f del x at x star times eta plus del 2f del x2 1 by 2 factorial eta square and so on. So this is just a Taylor series expansion. So we have performed a Taylor series expansion of this particular expression, and at the fixed point f of x star is 0. So this boils down to del f del x at x star times eta. So d eta dt is del f del x at x star times eta plus order eta square terms. So these are all higher order terms. And if eta is small, that is, if we are really looking into the neighborhood of x star, then eta will be quite small. because x is very close to x star. So the higher order term contributions will be small compared to the leading order term. So this particular term is the leading order term. So if we just focus on this particular equation, it says that 1 by eta d eta dt is equal to del f del x at the fixed point. And if del f del x is positive, then we have exponential growth. Okay, so if del f del x at x star is positive, then you have exponential growth locally. And if del f del x is negative, then you have exponential decay locally. And this is what we have physically seen over here. Here del f del x, so f prime x at this fixed point is negative, and so this is an attracting point because points nearby will decay, that is eta will reduce from this particular equation. As time increases, eta will reduce when del f del x is negative. For this point, as time increases, del eta del so the eta will increase, that is the difference between x and x star will increase. So this is a repelling point. Okay, so it's an unstable point. It is also, rather it is called as an unstable point, while this is a stable point, this is a stable point. And really, you don't need to go into all this algebra to really understand whether a point is stable or unstable. You can simply go by the same logic. If you start at this point, dx dt is positive, and so it will move towards a positive x. You start at this point, dx dt is negative, and so you go towards lower values of x. So what this small proof tells us that if del f del x is 0, then you have to look at the higher order terms. But geometrically, it is much more easier to see. So let us draw the condition where del f del x is 0, something like this. At this point, del f del x is 0 and f is also 0. So obviously this is a fixed point. But what happens over here? If we have this as an initial condition, x dot at this point is positive. So this point tends to go towards the right. If we have an initial condition over here, once again, the x dot is positive and it tends to go over here. So all the points on this side, they tend to go towards this. All the points on this side, they tend to go away from this. So it's called as a half stable point. Okay. It attracts half the points towards itself and it repels half the points away from it. I mean, not half the points in the sense 50-50, but one set of points it attracts, one set of points it repels. So in a 1D problem, it is called as a half stable point. So with this thing out of the way, let us move on to bifurcations. So often we will have conditions where the physics of the problem will be dictated by some controlling parameter. Okay, so let us have a look at the ordinary differential equation. X dot is equal to r plus x square. Now, this is a very famous prototypical problem. So the problem at hand is x dot is equal to r plus x square. So let us try to look at this problem from a geometric viewpoint. Let us try to find out the fixed points and their stability. So let us go to our Python console. Let me copy paste this because we will be needing all of this. All right. So now let us plot that diagram first. So x equal to np dot linspace minus 2 to 2, r equal to say 1, and x dot is r plus x square. Then we will do plt dot plot x comma x dot. So it looks something like this. For completeness, let us also plot the x-axis. So plt dot plot x comma 0 times x. Let us make it a black line. Alright, so we see that when r is positive, this curve does not cut the x-axis. So what is the meaning of this? When the curve does not cut the x-axis, it means there is no fixed point. Okay, so all the initial conditions over here, they will be accelerated towards the right. Because for all points, everything is headed towards the right. All the x dots at all these points are positive, and hence all the flows are towards the right. Let us make this interactive. Let me remove r. Let me pass r as a input to the function. So def c fixed points, and the input will be r. Let us set a default value of 1, and over here we will put everything inside the function definition, and we will say w equal to interactive. We will pass the function handle, and we will say r, it goes from -2 to 2 in steps of 0.2. We will display the widget. So this is the widget. So let me change r. Let me increase it. So obviously increasing it makes it go further towards the upper direction. So there are no roots. As I reduce r, we see that as we reduce r, there's a point when r equal to 0, there is exactly one point of intersection. That point of intersection is obviously x equal to 0. When r is negative, we will have 2 points of intersection, and so we have 2 fixed points. So when r is less than 0, we have 2 fixed points. So what are the values of fixed points? Let us see. At the fixed point, x dot will be equal to 0. So x will be equal to plus minus square root of minus r. So when r is positive, obviously there are no roots, no real roots. When r is negative, there will be 2 roots. When r is 0, there will be 1 root, which is x equal to 0. So what is happening as we are changing the control parameter r? So r can be interpreted as a control parameter. As we are changing the value of r from negative to positive, we are having a change in the fundamental behavior of the system. Okay, so if I draw on this axis r, and on this axis the fixed points, for r positive there are no fixed points. For r equal to 0, 0 is a fixed point. For r negative, there are 2 fixed points. Okay, so for r equal to this value, the fixed points are this and this. So there is a fundamental change in the behavior. As we cross r equal to 0, okay, r equal to 0 is a point, is a changeover point from having 2 roots to having no root. Okay, so here there are 2 fixed points, here there is 1 fixed point, and here there are no fixed points. Therefore, we say that the system has suffered bifurcation at r equal to 0, and the r critical is equal to 0. This kind of behavior is called as bifurcation, because by changing r, we are changing the fundamental characteristic of the equation. So this occurrence is called as saddle node bifurcation. And a saddle node bifurcation in this particular context makes no sense because saddle node bifurcation is more generally valid for phase portraits in 3 dimensions or bifurcation diagrams in 3 dimensions. So over here it is also called as a turning point bifurcation. It's called a turning point because we will see why it's called a turning point. So now x equal to plus minus root r is a root, right? So we know that they are fixed points, but what is the stability of the fixed points? So we have just seen that the stability depends on del f del x at the fixed point. So the fixed point, so the first fixed point is root of minus r, second fixed point is minus root of minus r, and the function f that we are plotting is this r plus x square. So df dx is going to be 2x. So f prime x. So remember, primes are spatial derivatives and dots are temporal derivatives. So f prime x is 2x. So it will be 2 square root of minus r and minus 2 square root of minus r. So when r is negative, this is obviously negative. When r is negative, this is obviously positive. So the positive root gives a positive value of the slope and hence it is unstable. So this particular branch is the unstable branch, whereas this particular branch is the stable branch. And in this particular case, we could find out everything analytically, but let us see how to implement this on Python. So we do have this function where we have wrapped it, and now we are more interested to find out the roots. So I mean, here analytically it's possible, but still let us make use of Python's libraries to find out the roots. So for that, let us import fsolve. So if you recall from the previous lectures, fsolve is a solver which finds out roots of nonlinear algebraic equations. So let us import that from scipy.optimize import fsolve. All right. So for using fsolve, we have to pass a function handle. So this particular thing has to be made into a function handle. So def f, and it will take as an input x, and it will return r plus x square, and let this function take as an optional parameter, not an optional parameter, as an argument r. Okay, so it will take the value of x and r and it will return me the fx that we have in the analytical expression. All right, so once we have this, let us say sol is equal to fsolve, the function handle f, the guess value. So let me put two guess values, one on this side. So let one guess value be minus 2 and let one guess value be 2. The arguments to the function, so args equal to r, and let us pass the full output to the solution. So we need the full output because we need to know whether there is a root found or not, because obviously for r positive there will be no root. So fsolve will say I did not find anything. So in order to assess that information whether it has been able to converge or not, it will pass all the information. In fact, let us take this in a different cell. Okay, let me copy this, let me go back to the previous cell. I don't want to disturb this cell. Let me go to a different cell. Okay, so let me make the correct, yeah. Okay, so let me run this and see if there's an error. So it ran properly. I have not get passed r from this cell. It is using the r from the previous cell. So let r be equal to 1. So now r is positive and we expect the solution to not have converged. So let us see what sol is. Okay, excellent. So it contains two values, and then it says that the iteration is not making good progress. Okay, so the meaning of this is it's not um, it's not able to converge properly. Okay, it's trying to do iterations, but it's finding nothing. So in that case, let us see what sol 0 is. It gives this. What sol 1 is, oh, sorry, what sol 2 is. It says 5. So the thing about fsolve is if it gives an output, the sol 2 object will be equal to 1. Okay, this particular value that it is printing, if it is not 1, it means it has not converged. And how do I know that? Let me double click on this and go to contextual help. Okay, so function x naught args. So this is how you pass everything. We can pass the Jacobian as well. We don't need to do that. It returns what? It returns x and the info directory. So this is the info directory that we just read. Number of function calls, number of Jacobian calls. We don't need all that. It outputs an error integer. It is an integer flag. It is set to 1 if solution is found. Otherwise, it will not return 1. It will return some other value. So it has returned to us a value of 5. It means the solution has not converged. Okay. So let us make use of that information. So after this line, we have obtained the value of sol. So if sol 2 is not equal to 1, or rather if sol 2 is equal to 1, then we should do something with it. So if sol 2 is equal to 1, let us classify the roots. Okay, meaning when I know that roots are there like this, I know that there are roots. Let me check the value of f prime x at those roots and classify those roots as being a stable fixed point or an unstable fixed point. Okay, so if sol 2 is equal to 1, this obviously means solution has converged. So now I don't know how many roots this has. Okay, I know in this particular question that I have 2 roots. In general, I will not know how many roots I have. So I must loop over sol 0, because look, sol 0 will, that number of elements of sol 0 will be the number of roots that fsolve has found. So then I will say for I in np.a range 0 to np.size of sol 0. So just to give you a context, np.size of sol 0 is equal to 2. If I had 5 roots, np.size of sol would have been 5. So I do a loop over all the roots. Okay, for I in this, what should I do? I should check the root. So root is equal to sol 0 I. So this is the root that we extract. So I will loop over all the roots, and sol root will contain iteratively the first root, the second root, the third root, the fourth root, the fifth root, how many number of roots you have. So after this, I will check slope at root is equal to df dx. I have to make a function df dx which will evaluate the slope of root. So let me make that function. Def df dx x comma r return 2 times x. Okay, So it will return the slope at the root. If slope at root is greater than 0, then I should plot it. So how should I plot it? I should plot as a cross because it's an unstable point. So plt dot plot. So I have to plot on the x-axis the r. So over on the x-axis I have to plot the value of r, and on the y-axis I must plot the value of the root, and I must plot it as an x. Let me make it as a blue x. Okay, else plot r comma root as a red circle. So if it's a stable root, it will plot a red circle. If it's an unstable root, it will make a blue cross. Okay, so let us see what happens. Okay, there's an error. Duplicate argument in function r. So this has to be x. Okay, so obviously there was no root, so there's no plot. Let me make r equal to -1. I have to pass two functions. Okay, well obviously we have made a small mistake. This should not be 2 star star x. This has to be only 2 times x. Okay, so let's run this. So obviously this is a unstable root as we have seen over here, and this is a stable root as pointed by the red circle. So now what do we need to do is to loop over various values of r and draw this entire diagram. So what should I do? I have to make r array is equal to np dot linspace -2 to 2, and I have to wrap everything inside a loop which will iterate over various values of r. So I must put everything inside here, over here inside a loop, inside a for loop. So for r in ra, then I have to indent everything because I want to execute this entire chunk of code inside the loop, and that's it. So let us execute this cell and see what happens. Excellent. So we do see, let me change the aspect ratio of the plot. So ax equal to plt dot gca x underscore set ax dot set aspect sets 2. Okay, and let us make the x limit all the way to the r range that we have. So plt dot xlim, it should go from minimum value of r to the maximum value of r. So np dot min of ra to np dot max of ra. So this is how the bifurcation diagram looks like. Let us plot the x-axis for completeness. So plt dot axh line, and let us put it at 0. So axh line is just a quick function for drawing a horizontal line passing through 0. Okay, so this shows us how the bifurcation occurs. As we are changing the value of r, let me make it 1. So as we are changing the value of r from left to right, we are going from a pair of roots, one unstable, one stable. We are reaching the critical value of r at 0, after which we have no more stable unstable points. Okay, everything vanishes. There's no fixed points in fact. So RC, which is 0, it indicates that once the parameter crosses this value of r, we will have no more fixed points. So this kind of bifurcation is called as a saddle node bifurcation. Okay, so this is how we can do it. Now all this is fine. I mean, it may appear that this is a very specific condition. I mean, why would I expect this kind of a ordinary differential equation to appear? Well, let us delve further into what is going on. So first of all, what is happening at the point of bifurcation? You have a function of x which looks something like this, and as you are changing the value of r, it, it reaches this critical condition where it is just becoming tangential to the x-axis. So for the saddle node bifurcation, we have what? We have fx vanishing. Okay, we also have, so fx vanishing is tantamount to that point being a fixed point. Okay, that's for sure. So we just have a fixed point which appears. Okay, and the other condition is it is tangential to the x-axis. So df dx must also be 0 at that crossover condition. So what was fx? So fx was equal to r plus x square. So for what uh, value of r does it happen? So df dx will be equal to 2x. So this has to be 0 and this has to be 0 at the point we achieve a crossover from two stable roots, from two fixed points to no fixed point. So when this is 0, it implies x equal to 0, and when we substitute x equal to 0 over here, so this is that fixed point which takes part in the bifurcation, and we substitute this over here, we obtain RC, that is the critical control parameter, to be equal to 0 as well. So r equal to 0 and x equal to 0 are like the critical pair. So RC equal to 0 is the control parameter critical, and it corresponds to x equal to 0, and this is the place where bifurcation occurs. So now it is not just this equation that exhibits such a behavior. Let us look at an example. Let us look at an example such as dx dt, or in fact let me write it as x dot t uh, is equal to e to the power um, r minus x minus e to the power minus x. Okay, let us try to see what the bifurcation diagram for this looks like. So because we have already written the code, we can simply modify our function and the derivative for having this kind of an output. So let me copy this entire cell. Let me make a new cell. This will be r minus x minus np.exp of minus x, and the derivative will be minus 1 plus np.exponential of minus x. So let me run this and see what happens. Well, we do have a bifurcation. What happens over here? What do we see? So as r varies from minus 2 to 2 at a certain value, so there are no roots so far, but after a certain point there are two roots. One is a stable root, the upper branch is a stable branch, the lower branch is an unstable branch. Okay, let us put those annotations as well. Let us have a look at the function. So xy string. Okay, so I need to pass the xy over here. So let us put the string at 0.5 and minus 1.2. Okay, so it's the unstable branch, and let me put another string on top which will say it's a stable branch. All right, so The stable branch and unstable branch are these, and there is a critical point somewhere over here. I mean, we could obviously increase the resolution of the R. So let us increase the resolution of RA. Let me take 200 points to pinpoint where that happens. Okay, actually it's very difficult to pinpoint by just looking. So what you should do is find out the first occurrence of R where this condition fails. Okay, where this condition fails. When this does not return 1, it means that it is not having two solutions. But the moment it starts returning 1, you have two solutions, or you have roots. Not just two solutions, but you have roots. I'm not going to do it right now, but you can try it when you have time. So it is clear that even this equation does have a saddle node bifurcation behavior. And why is that? Why does this equation also have a saddle node bifurcation behavior? Let us look deeply into how this equation reacts in the vicinity of the fixed point. So let us expand uh, this around x equal to 0. So x dot is r minus x minus, so this becomes what? 1 minus x plus x square by 2 factorial and so on. So this becomes r minus 1, this x cancels out, plus x square by 2 factorial. So obviously the first root that will occur over here is x equal to 0. So this expansion of the function that we're doing is near that bifurcation point. So near the bifurcation point, the equation behaves like this, and it has the same form. So x dot is some constant plus x square by 2. So it does have the same form. So obviously near the bifurcation uh, boundary, it has the same prototypical behavior as this particular equation. All right. So that is why studying such prototypical problems is quite important, and such a reduction of a problem in the vicinity of the bifurcation point is called as a normal mode, or a normal form, not a normal mode. The normal form for a saddle node bifurcation is this. Okay, is this. So this is a normal form for a saddle node bifurcation. So obviously there are different normal forms for different kinds of bifurcation, but for now we have only studied the saddle node bifurcation. Can we prove this rigorously? Can we prove that near the bifurcation point it will always reduce to a normal form? And the answer is yes. Let us take a quick look into that. So what are the conditions when the bifurcation occurs? So the conditions are that f of x has to be equal to 0, and df dx at x also has to be 0. Okay, so let us write down x dot is equal to f of x, and it is a parameter of r as well. So it is a function of x and r. So this can be written as f of x star comma rc plus del f del x at x star comma rc times x minus x star plus del f del r at x star comma rc r minus rc plus del 2f del x2 x minus x star whole square by 2 factorial at x star comma rc. Now by very definition of being a bifurcation point, fx will be 0. Essentially fx comma r will be 0. So x star comma rc will be 0 because that is the bifurcation point, and hence this term will vanish. Similarly, del f del x at x star comma rc will also be 0, and hence this particular term also vanishes. Obviously there are higher order terms, but because we are studying the behavior of this system near x star and rc, this is what we can write. And essentially x dot eventually boils down to del f del r at x star comma rc times r minus rc plus del 2f del x2 1 by 2 factorial times x minus x star whole square. And quite obviously you can obviously cast this as a times r plus b times x square, where a and b are various constants which contain all those various terms. So this has to be at x star comma rc, and hence these such equations under the conditions of a saddle node bifurcation do reduce to that kind of a normal form. Okay, so this is what I wanted to discuss about saddle node bifurcations. Before ending this lecture, let me also show you how you can geometrically think about this particular equation. Sorry, this, where is it? Yeah, where you can geometrically think about this particular equation. So, how do you geometrically find fixed points for this? Obviously, I mean, you can plot it and see, but it is comprised of two functions, r minus x and e to the power minus x. So, at the fixed point, x dot will be equal to 0. What that means is r minus x will be equal to e to the power minus x. The curve for e to the power minus x looks something like this. And r minus x is a straight line. And depending on what the value of r will be, we will have a family of straight lines which will look something like this. So now all we have to do is probe whether or not r minus x cuts e to the power minus x at one point, at no points, at 2 points, and so on. So when r has a large value, it cuts the curve at 2 points. So when r is large, obviously there are two roots, and this is something which we can corroborate with this diagram over here. When r is 0, this is what it will look like, and obviously there is no root. In fact, for quite some time there will be no root until it reaches this tangentiality condition. So when r minus x becomes tangential to e to the power minus x, we will have only one root, and that is the condition for bifurcation. It is going from no roots to two roots through that particular tangency condition. So at the point of bifurcation, we will have two things. One is the blue line intersecting with the yellow curve, that is r minus x will be equal to e to the power minus x. That is one condition. And the other condition is the slope of r minus x will be equal to the slope of e to the power minus x. Okay, so the slope of r minus x is equal to minus 1. The slope of e to the power minus x is equal to minus e to the power minus x. So what are the conditions under which this is satisfied? So this is satisfied when x equal to 0. This equation is satisfied when x equal to 0. And when we substitute x equal to 0 over here, we have r equal to 1. So r equal to 1 is the critical control parameter where bifurcation occurs, and the fixed point which corresponds to this particular bifurcation is equal to 0. Okay, so over here x equal to 0, so the y-axis is x, and r equal to 1 is the point where bifurcation occurs. So we can go ahead and plot that line as well. So plt dot av line axv line, and we have to plot it through 1. So that is the zone of bifurcation, and it is obviously separating two roots. One is a stable branch and one is an unstable branch. You can obviously write a nice slider function to check the presence of roots. I'm not going to do that. You can try it out on your own. You know how to do it by now. Okay, so this is all I wanted to discuss about saddle node bifurcations. In the next lecture, we're going to look into the other kinds of bifurcation, namely transcritical bifurcation and pitchfork bifurcation. Until then, it's goodbye from me. Try to experiment as much as you can. Experience is your best friend. Bye.